Video, we're going to review complex numbers. We'll look at two different types of dividing complex numbers, and then what happens when you solve a problem using either completing the square root method, or quadratic formula, and end up with complex solutions. So the first thing that we're going to do is look at dividing complex numbers where the denominator is a monomial. Because the denominator is a monomial, all we have to do to get rid of the I in the denominator is multiply by I in the top and I in the bottom. You're allowed to do that because I divided by I is 1. So it's okay to multiply by 1 if you need to. In the numerator, this is just going to be distribution. So negative 2 times I is negative 2I. And then negative 5I times I is negative 5I squared. In the denominator, you get 3I times I, which is 3I squared. And then every I squared has to turn into negative 1. Just the I squared turns into negative 1. So now we'll get negative 2I minus 5 times negative 1 and 3 times negative 1. This is going to simplify. Negative 5 and negative 1 makes positive 5. And on the bottom, we have negative 3. The proper way to write this is first to have the real number come first and then the imaginary number. So it should be 5 first and then negative 2I. But then to also divide these both by negative 3 separate. The first fraction stays as negative 5/3. And then the second one, the negative and the negative, turns into a positive 2/3 I. And that's an A plus BI standard form of an imaginary number. So the reason that we only had to multiply by I here was because the denominator was a monomial. The next type of dividing we're going to do is with a binomial in the denominator. So when there's a binomial in the denominator, we have to multiply by 5 minus 9i, which is what we call the conjugate. So you always choose the conjugate of the denominator. If the denominator is 5 plus 9i, we'll multiply by 5 minus 9i. And if we do that in the bottom, then we also have to do it in the top. Okay. In the numerator, we're going to FOIL because these are two totally different binomials that are getting multiplied. Negative 1 times 5 is negative 5. Negative 1 times 9i is positive 9i. Negative 6 times 5, negative 30i, and negative 6i times negative 9i gives us positive 54i squared. All right, and then in the denominator, you don't necessarily have to FOIL. You can just do the F and the L in FOIL. You don't have to do the outer and the inner, because the outer and the inner terms always cancel out when you're multiplying conjugates only. So we say we can use the FL method only with conjugates. So first, 5 times 5 is 25, and the last term is 9i times negative 9i, negative 81i squared. Every like term needs to get combined, and then every I squared needs to turn to negative 1. So it's two things that you have to do to simplify. So we'll get negative 5 minus 21i, and then this I squared will turn to negative 1, which gives us minus 54. In the denominator, again, this will turn to negative 1, so that gives us 25 plus 81. If you simplify, we have like terms, negative 5 and negative 54, which gives us negative 59 minus 21i. Remember, we always write the real number first, and then we're going to divide by 25 plus 81, which is 106. And I don't think that that simplifies, but if it does, then you would simplify. Okay. The next thing that we're going to look at is completing the square or using quadratic formula, where your answer is going to be an imaginary number. So You could also get imaginary numbers when using square root method, but this problem's not able to be done using square root method. So let's first choose completing the square, and then I can do it again using quadratic formula. So if I solve this problem, and I just said solve, what I would do first is try to factor by taking out a GCF. And you would try to do trinomial factoring here and ask yourself what multiplies to 7 and adds to 4, and nothing works. So it's not factorable. After trying that, I would decide that I was either going to do completing the square or quadratic formula, which we decided we would start with completing the square. The first step in completing the square is to move c over to the other side. And then divide every term by a so that there is no a value. And we get x squared plus 4x equals -7. The next step in completing the square is to take b, divide it in half, and square it. And we use the formula b over 2 squared for that. So b is 4, divided by 2 is 2, squared is 4. So that gets added to both sides of the equation. The left side needs to be factored. It'll always be a perfect square trinomial, which means that it's the same two binomials that multiply to make x squared plus 4x plus 4. And on the right side, you'll simplify. And you get -3. If you were to factor, you would get what multiplies to 4 and adds to 4, x plus 2, x plus 2. You have to write it as x plus 2 squared, or this is going to be a lot more difficult. So when you write it like that, you might notice that you can take the square root of both sides, and that's always going to happen. So we'll be left with x plus 2, because the square root and a squared cancel out. And on the right side, every time that we take the square root of both sides, you should get plus and minus. And the square root of 3, if you broke that up, would be square root of 3 times square root of -1. And we know that the square root of -1 is I. So it would be I square root of 3. Anytime you take the square root of a negative number, you have to include the I. You cannot leave a negative on the inside of a radical. To complete the problem, we're going to subtract 2 from both sides. And the proper way to write this is an a plus bi form, where the real number comes first and then the complex number. So it'll be -2 plus or minus I square root of 3. Or you could split it up and write it as x equals -2 plus I square root of 3 and -2 minus I square root of 3. Just make sure that your plus and minus goes in front of the radical term and not in front of the 2. 2 is negative either way. Now we're going to do the same problem but using quadratic formula. So 2x squared plus 8x plus 14. Again, the first thing that you would do would be try to factor. It's not factorable, so I don't even need to worry about taking out a GCF. We're just going to go right to quadratic formula, where a is 2, b is 8, and c is 14. The quadratic formula is x equals -b plus or minus the square root of b squared minus 4ac all over 2a. So if we fill that in with our information, x equals -b is 8 plus or minus the square root of b, which is 8 squared, minus 4 times a, which is 2, and c, which is 14, all over 2 times a, which is 2. And if we simplify, we always simplify what's inside the radical first using PEMDAS. So x equals -8 plus or minus the square root of 8 squared is 64. And then if you want to skip ahead and multiply here, you can do that at the same time, but you could also write it out twice. So you're going to do -4 times 2, which is 8, times 14, which is negative 1/12, all over 4. If you notice, I'm already going to get a negative in the radical, which is just because we already know that there's going to be an imaginary solution here. So x equals negative 8 plus or minus square root of negative 48 all over 4. Either way, even though you're getting an imaginary solution, you'll need to break down 48 into 1 and 48, 2 and 24, 3 and 16, 4 and 12, 5 doesn't work, 6 and 8, 7 doesn't work, and 8 we already have. So 3 and 16, 16 is the largest perfect square. I'm going to write it as x equals negative 8 plus or minus the square root of negative 16 times 3. And the reason that I put the negative on the 16 is because that's the number I'm taking the square root of. So hopefully it reminds you that you're going to need to include I. So all over 4. We'll simplify x equals negative 8 plus or minus the square root of negative 16 is 4i square root of 3 all over 4. And just like we do in completing the square, we're going to write this out as separate fractions. Negative 8 over 4 plus 4i square root of 3 over 4. Negative 8 over 4 simplifies to negative 2 plus or minus I square root of 3. X equals, which is the same thing that we had when we did completing the square. So either way, you get the same answer.